work is about energy materials and thin films, and we are focusing on development of novel materials to address challenges in materials for batteries and photoelectrocatalysis. So, as photoassisted ALD is most likely quite new to most of you, there are typically quite a few questions when this is mentioned for the first time. So what is it and how to do it? And since light is directional inherently, are the films produced with that then conformal on 3D structures? And since the chemistry is slightly unorthodox, considering the traditional ALD, are the films pure? Is it really the material that you're claiming? And most importantly, can you do area-selective deposition by masking? So can you transfer patterns with the light through a mask? And is it ALD after all, or at all? So photo ALD, what is it? It's, of course, matter of definition, and we've defined it so that it's photons in UV or visible range that introduce energy into the ALD system by creating electronically excited states in the valence band of the solid material or in the valence orbitals of the precursor molecules or adsorbents. And since ALD is sequential, as we all know, and light is directional, that gives a few possibilities to play around on what you actually expose the light with. So you can, by having the light only in the gas phase, and during the precursor pulse, you can excite only the precursors in the gas phase. Or if you do the light exposure during the purge, then you don't have any reactive species in the gas phase, then you can excite only the precursor adsorbents, and of course you expose the film and the substrate. Whether there is any photoprocesses, that's another question. Or if you do it during the pulse, then you excite the whole system, including also the precursors in the gas phase. So photons bring energy to the deposition system. That's photo ALD all about. Here are a few selected examples from the literature on processes utilizing photons, or ALD processes utilizing photons in different flavors of it. So this is quite recent. So in that case, well, they expose the oxygen gas to UV photons, and then basically you get excited states for the oxygen, and then it's more reactive than the molecular oxygen. And then there are different, well, basically all these aspects that were presented on the previous slides have been explored with different kinds of materials. So this work on the following slide is based on an outcome of a 3-year project that we had at University of Helsinki, where I was working previously. And these results, or these data that we have that I present, it's just basically cream on the top of it. So we had 3 years of time, and believe me, it was quite a lot of experiments with no success. So we had Picosan reactor that we modified in collaboration with Picosan, so that we could introduce the light. So you need the lamp for it in the first place, and also some optical window that you can isolate the vacuum system, the reaction chamber and the vacuum chamber from the light itself. And then you need to make sure that there is no growth on the optical window because eventually that the deposited film would block the UV. So we had a nitrogen curtain to flush diffuse silica window. And one of the lamps that we used was xenon discharge lamp. So that has very broad emission spectrum ranging from 190 or so to tailing towards the IR. So it has it's basically artificial sun. Then we had another lamp. It was a deuterium lamp, and that is different to this. So this is pulsed lamp. So that then you can, it's like built in to be used for ALD because ALD is pulsed. So then with this pulsing function of the lamp, we can also pulse or put the exposure of light in places of the recipe we want. But this deuterium lamp is continuous emission, so then we have to have a gate valve and different optical window in order to have a best possible transmission. And we changed the gas also because nitrogen has emission around 130. Of course, it's low pressure gas. The absorbance wouldn't be too high, but we wanted to make sure that the gas remains inert also in photo ALD conditions. Then few results on successful depositions with photo ALD. So this process had been already published by a Korean scientist. So we took this as a proof of concept for our reactor. So we used tantalum ethoxide and then used this sequence. So we basically eliminated the substrate, the film, and the precursor adsorbents. And this process works from 150 to 45, and it shows the usual characters of an ALD process. So it saturates, also regarding the flashes from the UV lamp. There is a temperature dependence for the growth rate. It is lower than from thermal ALD. So with water, this deposits at around 0.4 angstroms per cycle. So it's lower because it's certainly different chemistry, but also we bring all the elements of the film with the alkoxide. And this alkoxide single source approach works for other metal oxides made from alkoxides. Basically, we tried all the volatile metal alkoxides that we could purchase. So in addition to tantalum oxide that deposits amorphous films, we deposited niobium oxide, also titanium dioxide that, by the way, produces rutile titanium dioxide in contrast to anatase base that is obtained from the thermal process with water from this. And also zirconium and hafnium tertput oxides. And zirconium oxide had this cubic phase mixed with the monoclinic. So cubic phase is of course the desired one because it has the highest permittivity for the applications in the gate oxides. And they were also quite pure, I would say, considering the process approach. So very low amount of impurities. And stoichiometry also based on this data by Ph.D. So it quite close to the stoichiometric proportions. Of course, slight offset because of the impurities present. Niobium oxide was actually slightly oxygen deficient, and that affected also the electrical properties of that, and also the density. And here's the QR code if you want to scan it and check the original paper. You can find more details about this. And then we also deposit copper using amino alkoxide precursor with similar single source approach. So we had this precursor Persian UV after that. Also reaching saturation around the same growth rate as for the oxide, tantalum oxide. These copper films were also quite pure. So this is depth profile with different elements present in the film. And this was deposited on tantalum oxide film. So that's why we have tantalum and oxygen enriched on the silicon copper interface. And then we explored quite a lot of different metals. We're aiming at depositing them with this approach. Somewhat we were successful with ruthenium, and this worked with both of these lamps. We had a precursor that contains ruthenium in oxidation state 0, so it's cyclohexadiene molecular ligand, and then 3 carbonyls connected to that. And that works at 125. Above that, it starts to thermally decompose. It deposited film, but it was quite full of impurities. So we didn't continue that. And then very similarly to copper, we managed to deposit nickel with the same single source approach. So nickel DMAP, so it's the same precursor as we use for copper, only with nickel this time. And this is still, we had 1 or 2 depositions, and we didn't study the material very carefully, but with XYD we could see that it's nickel. So as was presented on the first slide, light is directional, and maybe conformality is an issue here. So for tantalum oxide, we studied this. We had a pillared silicon substrate, so this pillars etched onto a silicon, and the sequence was with the number of cycles that we expect 50 nanometers film on a flat substrate. And on the bottom of this pillar, this forest of pillars, we get this 50 nanometers. But then on the walls of these pillars, it's wrapped around, so it's coated throughout, but it's only 20 nanometers on the walls of these pillars. But I would consider that this can be further optimized because the surface reaction absorbing the alkoxide in the precursor pulse that is producing a self-limiting saturated monolayer of that. And then if we only optimize this by exposing for a longer time, because on these walls the aerial exposure of the UV is much lower than on the surfaces perpendicular to the light beam. So there are no fundamental reasons that it couldn't be deposited as 50 nanometers on these pillars. As long as we can get light onto the surface, then we can get it deposited. On copper, we did similar experiment and found quite similar things, so that it's there on these pores, but it's slightly thinner on the walls. Lamp emission spectrum is broad, so what is the band of photons that does the actual chemistry? So for this we did simple optical filtering of the light beam. So we placed, this strip of silicon is sitting on the wafer, and then on top of that we put different glasses so that there is a gap between these glass slides and the substrate, so the gases can go there and do the absorption. And then we did the photo ALD, where these filter parts of the emission spectrum, and these have cutoff wavelengths around 300 nanometers, depending on the glass grade and the manufacturer. So we found that both of these glasses block this growth, which means that this end of the spectrum is responsible for the reactions depositing the material. Similarly, for copper, we did this experiment now with soda lime and quartz that has cut off at slightly shorter wavelengths. And for that, we found that, yes, still the soda lime cuts off also the growth, but with quartz, we get the film, but seemingly as a thinner thinner version than the rest of the substrate. So this blocks only little of the effective wavelengths. So we can get to a similar conclusion that it must be around this area and the shorter wavelengths that does the deposition reactions. Then shadow masking, we did a very rough mask. So this is just carved into a thick plate of aluminum. And then 2 deposition experiments, and we get this University of Helsinki emblem. Resolution isn't that great. And for copper, for the same thing, but still wanted to show this because this we thought that was most interesting one. So we found that the underlying film or the underlying substrate has quite critical role on this processes. So for some reason, we don't know yet, ALD tantalum oxide was the magical material where the copper did grow. So we did this kind of patterning with fib and wet etch. So we get like exposed tantalum oxide surrounded by aluminum oxide hard mask, and then we did photo ALD experiment on that, and then we very cleanly and very selectively grow copper only on the tantalum oxide. So there are no masks involved, just inherently self-aligned growth. And aluminum oxide really kills this growth. So it's thinning. This is thinning towards the opening of tantalum oxide because of the etch process. So wherever there is even a slight amount of amount that we can see with SEM, it kills the photo ALD. And on titanium dioxide, we saw that it's somewhat crystal facet selective growth. But since I'm ran out of time, so I won't be discussing more about that. All right, that's it. Since
Thank you very much. Super cool. So who has questions?
I would have a question. Thank you. It's a nice talk.
Mm-hmm.
I think it was slide 14 on the to me surprising thickness variation, 20 versus 50 nanometers. 50 on the bottom. Yeah, I think it was this one. Yeah, 50 nanometers on the bottom, 20 nanometers on at the top. And then I was wondering, could you comment on thermal diffusion from the bulk silicon substrate, maybe dominating to get that thicker layer, as compared to the 20 nanometers being photonically excited? Are there more than one? Well, is that more than just photonic effects? And also thermal diffusion.
Yeah, that's. I would say we can exclude that possibility with this result, so that because when we block or filter out basically this part of the emission spectrum that is minimal to the rest of the emission, we can cut off all the deposition. So if there was any photothermal effect, it would arrive from this part of the spectrum too, and we would only minimally decrease the growth rate with this experiment. But since it kills it completely, so it must be this part of the spectrum that is at least mostly responsible for the photoreactions in the system.
I think it's actually very easy to understand, because you have the light on the side coming close to the Brewster, or further than the Brewster angle. So you're focusing it reflects at the bottom of the.
That's a line of sight effect or so.
No, because the angle of incidence, the angle of incidence of the light on the side is at an angle where there's very high reflectivity of the Brewster.
It's 50 something degrees thing, yeah. Another question, more general. Of course, it's very well known that the surface energy of metals is so high that they always tend to ball up, which also reflects in your attempts, whether it was copper or some other metals. Yeah, this sort of thing. At what sort of film thickness did you get pure film closure?
Good question. It's around at, I think it requires, like, to get all these gaps sealed, it takes as high as 5,000 photo ALD cycles.
So pretty.
And the thickness is then around maybe 70 nanometers, depending on
Yeah.
where on these humps you
All
count
right.
these.
Any experience or sort of suggestions for the other people to in terms of pre-treatment and to get the or pre-wetting tricks that are around, so that you can have even, let's say, real thin layers being closed as a metal.
Of course, you could also decrease the deposition temperature, but that would also kill the growth.
I have two questions / remarks. So the obvious question is, what would it not be very much interesting to use an excimer laser or a quadrupole Yagi? Because then you have only UV. And in fact, that's an obvious comment, but I think what the additional feature that the laser can give you is that you could put most of your substrate below the ALD window, and you locally heat it with your laser, so that where your laser is, you are in the ALD window, and the rest stays cool. You have a
adiabatic locally.
That you don't have a photo dissociation of your precursor molecules, but you kind of locally bring the substrate in the ALD window and with the laser, and the rest of the substrate remains below it, and you have no deposition. Can you comment on that?
Well, silicon is quite good heat conductor as rest up, so I don't know how locally that would remain actually.
Well, people do, like for example, laser anneal with in TFTs for panel displays.
Yep, it's long for decades.
Yeah, but still, so if you want to do patterning with a UV laser with photochemistry, then you can get a lateral resolution of 1 micron or below. Whether if you use it just to locally heat up, then that will just decrease the lateral. Yeah. Both are possible.
I think that's
so. I'm trying.
In the round table.
Yeah, exactly. I'm trying to keep track of time. There is a question online. The question is whether photo ALD can help with controlling morphology. I'm not sure. The question doesn't say whether it's related to a better nucleation or better surface properties, and that might be able to prevent de-wetting. But can you? I guess the question is, can you influence morphology using photo ALD?
Yes. Yeah, sure. As at the moment, it's still, these are very first results, and what we can do, we can deposit with these process approaches, how to get control over different varieties of the material. That's still to be explored.
Okay. All right.
Do you think
a short one?
Do photo reduction with some of these films, like the pentoxide, for example? Just what do you think about that possibility or that prospect?
Well, for this, first of all, because it's obviously the photo process is because it's taking place in the substrate, so it's some sort of a photocatalysis, and then there is also reduction of the copper in the precursor, and then when something reduces and something must oxidize, and then it must be the ligands.
I guess my question is, so if you start with, say, a tantalum pentoxide film and you reduce that?
Not at these conditions. Well, for niobium oxide, we actually, as I mentioned, it is oxygen deficient, and it was denser than bulk NB205. So then there is
could be able to tune the stoichiometry of that.
For niobium oxide, yes, because actually it didn't fully saturate with the UV photons, so there was a slight slope, and well, we didn't study it systematically, but since this is reduced, so then probably the UV exposure time can be used for tuning the stoichiometry and the oxidation state of niobium.
We'll have a break.
Cool. I will do a break.
A break of 10 minutes. Yeah.
Okay. Thank you very much then.
Thank you.
I look forward to seeing the patterns. And there's going to be a lot of opportunities for chemistry here as well.
Yes.